So this is session 5 of module 3. In this session, I'll be talking about one of the supervised learning method, that is decision trees. We'll discuss what its structure, how it works, and different parameters for its construction, etc. So a decision tree is basically a type of supervised learning algorithm. That means it works with the data where we already know the target or the label we want to predict. It's most commonly used in classification problems, for example, deciding whether an email is spam or not spam. Now the nice thing is decision trees can handle both types of data, categorical like yes or no or male or female, and continuous like numbers such as age or salary, etc. The way it works is by splitting the data step by step. Each time it chooses the most important factor, what we call a splitter, and uses that to divide the data to smaller and more similar groups. In the end, you will get groups or nodes that are much more homogeneous. So you can see in the diagram below how the tree branches out at each decision point until it reaches the final outcomes. So here we can see how the decision trees are generating classification rules. So on the left you can see a decision tree diagram. It starts with the question, what is the temperature? If the temperature is not between 273 and 373 Kelvin, then the survival is immediately classified as difficult. But if the temperature is okay, then the tree checks the next factor, is the water present. If there is no water, again survival is difficult. If water is present, then we check for flora and fauna. If flora and fauna are missing, survival is still difficult. But if they are present, then we go one step further. We check if the surface is stormy. If it is stormy, survival is difficult, but if it is not stormy, then survival is considered as probable. On the right side of the this particular tree, you can see the same logic written out as classification rules. For example, rule 1 says if the temperature is not between 273 and 373 Kelvin, then the survival is difficult. Then rule 4 says if temperature is okay, water is present, flora and fauna are there, and there is no storm, then survival is probable. So basically each path from the root to a leaf node will give us one classification rule, and the final leaf nodes represents the output class. In this case, whether the survival is difficult or probable. These are the output classes. Okay, now let's make this idea more practical with an example. Imagine we have a group of 30 students. For each student, we have 3 pieces of information: their gender, whether they are in class 9 or 10, and their height, somewhere between 5 and 6 feet. Out of these 30 students, 15 actually plays cricket in their free time. Now the problem we want to solve is, can we build a model to predict who will play cricket during leisure time? So to do this, we need to separate the students who plays cricket from those who don't based on the most important input variable. But which variable should we choose, or should it be gender, class, or height? This is where decision tree comes into picture. The tree looks at all these 3 variables and tries splitting the students in different ways. It then picks the variable that gives the clearest separation. In other words, the one that creates the most homogeneous groups. So if you look at the diagram, you can see that splitting on gender gives the cleanest separation compared to splitting on height or class. So boys and girls shows a stronger difference in cricket playing compared to other variables. So the decision tree identifies gender as the most significant variable for the first split. Later it can still use height or class for further splits, but the first step is to choose the variable that reduces the mixture the most. And that leads us to the biggest question that is written here at the bottom. How does the decision tree actually decide which variable and which split to use? So that is what we are going to explore in the coming slides. Now the decision trees can actually be of 2 types, and that depends on the type of target variable we are trying to predict. So the first one is a categorical variable decision tree. This is when the target variable is categorical, basically a yes or no kind of outcome. For example, in our earlier student problem, the target was, will the student play cricket or not? So that's a simple yes or no answer which makes it categorical. And the second one is a continuous variable decision tree. Here the target variable is not a category but a number, something continuous. For instance, suppose an insurance company wants to predict a customer's income. So the company might not always have the income details, but it can estimate it based on other informations like the customer's occupation, the kind of product they purchased, and other related variables. So since income is a number and not a yes or no value, this becomes a continuous variable decision tree. So in short, if your output is like yes or no, male or female, play or not play, it is categorical. And if your output is a number like income, salary or age, it is continuous. So before we go deeper into decision trees, let us quickly understand some basic terminologies. First is root node. So this is the very top node of the tree. It represents the entire data set or population before any split happens. Then splitting, it is the process of dividing a node into two or more smaller nodes based on some condition. And decision node, if a node keeps splitting into further nodes, we call it as a decision node. Leaf or terminal node, these are the nodes that don't split any further. They represent the final outcome or decision. And pruning, just like trimming a tree in real life, pruning means removing unnecessary branches or sub nodes from a decision node. It's basically the opposite of splitting and it helps keep the model simple. Now branch or subtree, it is a section of the entire decision tree called a branch or sometimes a subtree. Then parent and child node, whenever a node is split, the original node is called the parent and the resulting nodes are called the child nodes. So these are the building blocks of decision trees. Now next is why decision trees are so popular and widely used. First, they are very easy to understand. Even people without a statistics or a math background, they can interpret them because the output is like a simple flowchart and the graphical representation is very intuitive and users can easily relate it to their own thinking process. Second, the decision trees are usually useful in data exploration. They help us quickly identify the most important variables and how the different variables relates to each other. In fact, they can even help us create new features with better predictive power. So if we are working with hundreds of variables, the decision tree can quickly tell us which one is actually mattering the most. Then third is they requires lesser data cleaning compared to many other models. Decision trees are not heavily affected by outliers or missing values, which makes them quite robust in real world data. And fourth, they can handle both the numerical and categorical data types. So whether your variables are numbers like age or income or categories like male or female, they can work with both. And finally, decision trees are considered non-parametric methods. That means they don't assume any specific distribution of the data or any particular structure for the classifier. So this flexibility makes them very powerful in different situations. Next is the disadvantages of decision trees. The first one is overfitting. So one of the biggest challenges with decision trees is overfitting. This happens when the tree becomes too complex and learns not only the real patterns in the data but also the noise. So as a result, it performs very well on the training data but poorly on the new or unseen data. So to handle this, we usually apply techniques like pruning, like trimming down unnecessary branches or setting limits on the tree growth. For example, a maximum depth or minimum samples per split. And next one, it is not the best for continuous variables. Decision trees can struggle a bit with continuous numerical data. When they split such variables, they break them into intervals like greater than 5 or less than or equal to 5, which may cause loss of detailed information. Unlike some other models like linear regression, they don't directly use the continuous nature of the variable in its full form. Okay, now next is how does a tree-based algorithm decides where to split? So okay, now comes the biggest question: how does it decides the split? So the quality of these splits makes a huge difference in the tree's accuracy. The main goal is always the same: to make the resulting groups or subnodes as pure and homogeneous as possible. In other words, after each split, the tree tries to make sure that the nodes contains the data that is very similar with respect to the target variable. So every time a split is made, the purity of the nodes increases. Now here is what actually happens. The tree looks at all available variables, and for each variable it tries out different possible splits. Then it chooses the split that results in the most homogeneous subnodes. The way the splitting decision is made depends on the type of target variable, whether we are working with classification or regression. And to do this, the decision trees don't rely on just one method. In fact, there are several algorithms used for splitting, and the most common ones are ID3, which stands for Iterative Dichotomizer 3, C4.5, CART, that is short for Classification and Regression Trees, and CHAIT, which is chi-squared automatic interaction detector. So each of these uses a different mathematical criterion to decide the best split, but the main idea is the same: find the split that creates the purest groups. So first we need to know the concept of entropy. So think of entropy as a way to measure messiness or disorder. Imagine you have a basket of fruit. If all the fruits in the basket are apples, then the basket is very pure or clean. There is no mess or mix up at all. In data science terms, this basket has zero entropy. Now what if we have a basket with an equal number of apples and oranges? If you reach in, you have no idea what you're going to get. It's totally mixed up. So this basket is as messy as it can be, and it would say it has the highest possible entropy. So in simple terms, entropy is our way of quantifying how mixed up our data is. And here is the formula breakdown of entropy. So in this S means it just stands for our data set, and C, it is the number of different types of things we have. In our case, the slide shows we have two types, positive and negative. So C is equal to 2. And Pi, it is the probability of picking one of those types. It's just the number of items of one type divided by the total number of items. Now here there is an example on the slide. You can see we have a data set with 100 data points. Among that, 30 are positive and 70 are negative. So the probability of getting a positive is 30 by 100 or zero point 0.3, and the probability of getting a negative is 70 by 100 or 0.7. Now we just plug those into our formula. E of s is equal to minus zero point 0.3 log to the base 2, zero point 0.3 plus 0.7 log to the base 2, 0.7. So when you do the calculation, you get a value of approximately 0.88, and this number tells us that our data set is pretty mixed up. It's not perfectly random, which would be an entropy of 1, but it's far from perfectly clean, which would be an entropy of 0. So now why do we care about entropy? Because our goal in machine learning is to build a model that can reduce uncertainty and make good predictions. So this is where information gain comes in. Information gain measures how much a particular feature or a question reduces the entropy of our data. We want to find the question that gives us the biggest gain in information, which means it helps us sort our data into the purest possible groups. So here is the formula of information gain. Ig of y comma x is entropy of y minus entropy of y given x. So we can say that information gain is entropy of parent minus weighted average into entropy of children. So entropy of parent means it is the entropy of our starting data set. For our example, it is 0.88. We just calculated now. Now entropy of children, this is the weighted average entropy of the new groups of data after we have splitted them using a feature like is the fruit red. So the weighted average part is important because it accounts for the size of each new group. So this decision tree algorithm is smart. At each step, it looks at all the possible features it could use to split the data. For each feature, it will calculate the information gain, and the algorithm then chooses the feature with highest information gain to make the split. By repeatedly choosing the best split, the decision tree efficiently organizes the data into clean, well-defined groups, allowing it to make accurate predictions. Now here we are going to use a great example to understand entropy, which is a key concept for building decision trees. So the image shows a contingency table, which is just a way to summarize our data. In this example, we have a total of 14 observations, and our goal is to predict the liability of a person, which can be either normal or high. To do this, we are using one feature called credit rating, which has three possible values: excellent, good and poor. So looking at the totals, we can see that we are having 7 observations in the normal liability class and 7 observations in the high liability class, because we have an even split. 7 and 7. Our initial data set is at its maximum level of disorder or uncertainty. This means our starting entropy will be as high as it can be. So we are going to calculate the initial entropy using the entropy formula. That is minus sigma is equal to 1 to c pi log to the base 2 pi. So here pi is the probability of an observation belonging to a specific class. So probability of normal liability is 7 by 14, which is 1 by 2, and probability of highest liability is 7 by 14, that is again 1 by 2. Now we will plug these probabilities into the formula and we will get it as 1. So the result 1 confirms that our initial data set has the highest possible entropy. So this makes perfect sense because the classes are evenly split, meaning we have the maximum amount of uncertainty about which class a new observation will belongs to. And this initial entropy value is what we will use as a starting point to calculate information gain, which tells us how much we reduce this uncertainty by splitting the data. So here we are going to calculate the entropy for each child node. So first we calculate the entropy for each of the 3 groups or child nodes, which is created by the split on credit rating from the previous step. So first is for excellent group, then for good group. So excellent group, there are 4 observations and 3 normal and 1 high. And for good group, there are 6 observations in this, 4 normal and 2 high. Then poor group, there are 4 observations with 0 normal and 4 high. Then after that, we'll calculate the weighted average entropy. So the excellent group is having 4 observations out of 14. So its weight is 4 by 14. Good group is having 6 observations out of 14. That is weight is 6 by 14. And poor group has 4 observations out of 14. So the weight is 4 by 14. And we'll finally calculate the information gain by subtracting the weighted average entropy from the initial or parent entropy. So as shown in this previous example, the initial entropy of the liability variable was 1. So that is by 1 minus 0.625, we get it as 0.375. So the information gain of 0.375 tells us that splitting the data by credit rating reduces the uncertainty by this amount. So in a decision tree algorithm, we would repeat this process for all other available features and then choose the feature with highest information gain to make the final split. So next we'll see a question based on decision tree. So here an initial data set is given. This is our main data set. It's about playing tennis based on the weather conditions. So we have total 14 days of observations and our target variable is play tennis. So which is either yes, which is positive, or no, which is negative. So let us count them up. There are 9 yes days and 5 no days. So our first step is to calculate the entropy for this entire data set. This tells us the initial level of disorder before we have split on any features. So the entropy for the whole data set is calculated as, and next we will be evaluating other features like temperature. We follow the same process. Find the entropy of each temperature group, hot, mild and cool. Calculate the weighted average entropy and then we will find out the gain. And gain of S comma temperature, that is 0.029. So this is a very low gain, meaning temperature doesn't do a good job of splitting our data cleanly at the top level. The next is humidity. Here gain we got is 0.15. This is a better gain than temperature but not as good as outlook. Then again we go for wind. Now how to choose the best split? For all the gains calculated for outlook, humidity, temperature and wind, outlook is having a higher value of 0.24. So it is chosen as the root node of our decision tree. Now what is outlook? Again we have to continue the tree. Now outlook is having three values: sunny, overcast and rain. So we have to go for each of these branches. The overcast branch is the leaf node because its entropy is 0. It's perfectly pure. So we can stop here and say if the outlook is overcast, then we will definitely play tennis. And the sunny and rain branches, it still have some disorder. So we need to repeat the process for these branches using only the data points in that particular group. So first we'll go for splitting the sunny branch. So we can focus on 5 sunny days. We have to figure out which temperature. Temperature that is temp, which feature that is temp, humidity or wind. So that gives us the best split for this subgroup. So first is about humidity. Splitting the sunny days by humidity gives us a clean split. The high humidity group has three numbers, three no's and 0 yes. So entropy is 0. And the normal humidity group has 0 no's and 2 yes. So entropy is again 0 and information gain is calculated as gain of S sunny humidity. So in that case we got 0.97, that is a perfect gain. And next is for temperature, we are getting a value of 4.57, that is again a good gain, but it is not as good as humidity. And next is for wind. For wind we are getting some 0.192, that is a very low gain. So because humidity has the highest gain of 0.97, it becomes the next split in our tree for the sunny branch. This leads to two leaf nodes. If the outlook is sunny and humidity is high, then the answer is no. And if the outlook is sunny and the humidity is normal, then the answer is yes. Now we go for splitting the rain branch. So first, finally we look at the rain branch, which has 5 days, that is 3 yes and 2 no's. 3 yes and 2 no's. We need to find out the best split here using the features temp, humidity or wind. So next, for temp, the gain is 0.192. The same calculations is repeated just like we calculated for the sunny branch. Then next is for wind, we are getting 0.97 as the gain value. So if the outlook is rain and the wind is weaker, then the answer will be yes. And if the outlook is rain and wind is strong, then the answer will be no. Next is Gini index. So both Gini index and entropy are ways to measure the impurity or disorder of a data set in a decision tree. While they are calculated differently, they serve the same purpose to help the decision tree algorithm find the best way to split the data. So Gini index or Gini impurity, it measures the probability of a randomly chosen item being incorrectly classified if you randomly assign a label based on the distribution in the dataset. A Gini index of 0 means the dataset is perfectly pure and all items belongs to a single class. A Gini index of 1 means the items are randomly distributed across various classes or perfectly impure. A Gini index of 0.5 indicates an equal distribution of elements across the classes, such as a 50 by 50 split. So here is the formula: 1 minus sigma I is equal to 1 to n pi square. So here pi is the probability of an item belonging to a particular class. When building a decision tree, the goal is to choose the split that results in the least Gini index in the resulting child nodes. So information gain is mainly used by the ID3 algorithm, and previously we have discussed the ID3 algorithm using information gain calculation to construct the decision tree, and this Gini index is mostly used by CART algorithm because they want to create binary splitting into only 2 child nodes at a time. So next we can see an example of Gini index. So this slide is showing a data set with 10 observations where the goal is to predict if the return will be up or down based on 3 features: past trend, open interest, and trading volume. So the decision tree algorithm will test each of these features to see which one provides the best split. It does this by calculating the Gini index for each feature. A lower Gini index indicates a more pure or less mixed split, which is what we want. So here it is the Gini index calculation for past trend feature. So the data is splitted. Past trend is having two values, positive and negative. Calculate the Gini for positive. Out of these, 4 have written up and 2 have written as down. So the probabilities will be 4 by 6 and 2 by 6. And Gini is 1 minus 4 by 6 square plus 2 by 6 square, that is 0.45. And now calculate Gini for negative. For all 4 is having written down, so that is a perfectly pure group. So probabilities are 0 by 4 and 4 by 4. So Gini is 0 here. Now we calculate the weighted Gini. We combine the Gini of each group weighted by its size. There are 6 positive observations out of 10 and 4 negative out of 10. So Gini of past trend is 0.27. Next, we calculate the Gini index for open interest. That is, repeat the same process here also. So split the data. Open interest is having two values, high and low. Now calculate Gini for high. Out of these, 2 have written as up and 2 have written as down. So that is a 50 by 50 split. So Gini is 0.5. And then calculate Gini for low. Out of these, 2 have written as up and 4 has written as down. So Gini is 0.45. Now calculate the weighted Gini. So the Gini index for open interest is 0.47. Now next we calculate Gini index for trading volume. So trading volume has two values, high and low. So calculate Gini for high. So out of these, 4 have returned up and 3 have returned down, and Gini is 0.49. And again calculating Gini for low. Out of these, 0 is having return up and 3 are having return as down. So that is perfectly pure group. So Gini is 0. Now weighted Gini is 0.34. So what is the final decision? The final decision is we are having a Gini index for all these features. Past trend is 0.27, open interest 0.47, and trading volume is 0.34. So the decision tree algorithm chooses the feature with lowest Gini index because it results in the purest split. So in that case, past trend is chosen as the lowest Gini index. So that will be the root node to start the building of tree. Now next is about tree pruning. So before going to tree pruning, we have already learned what is overfitting. So tree pruning is the solution to overfitting. It is the process of simplifying a decision tree by removing the less important branches and nodes. So think of it like trimming a bush to give a clean, simple shape for it. So we use statistical measures to identify and remove the branches that are least reliable, meaning they are likely just reflecting quirks in the training data rather than a true pattern. So why we are pruning a tree? It is simpler and faster. A prune tree is smaller, less complex, and easier for us to understand. It also makes the predictions faster, and there is better generalization. That is the most important benefit, is that a prune tree is much better at correctly classifying independent test data. By removing the noisy branches, it focuses on general core rules, which leads to better performance on real world data. So pruning a decision tree helps us to create a model that is not only more efficient but also more accurate in the long run. So next is two main approaches to tree pruning. One is pre-pruning and the other one is post-pruning. So pre-pruning means it stops the growth of the decision tree early. It's like deciding not to plant a tree in a certain spot because you know it's going to grow too big. So how it works? As a tree is being built, the algorithm checks a stopping condition before splitting a node. A common condition is a threshold on the goodness measure like information gain or Gini index. If a split would not result in a significant enough improvement in the purity of the nodes, that is, if it is falling below a particular threshold, then the algorithm stops splitting that branch. So the result is that the node that would have the split becomes a leaf node. So this leaf is then labeled with the most common class among the data points it contains. And the challenge here is to choose the right threshold. So that can be tricky. A threshold that is too high, it can stop the tree's growth too early, leading to an oversimplified model. And a threshold that is too low, it might not simplify the tree enough. The next is post pruning. So it involves building a fully grown or a complete decision tree first and then trimming it back. It's like letting a bush grow wild and then carefully cutting it into a cleaner shape. So how it works? The algorithm will remove branches from the complete tree starting from the bottom. It replaces the whole subtree, a branch and all its nodes with a single leaf node. And the result will be the new leaf node is labeled with the most frequent class from the data points in the removed subtree. For example, the CART algorithm, it uses a cost complexity pruning approach, which is a form of post pruning. So this method finds the right balance between tree's complexity and its accuracy. So pre-pruning, it stops the tree from growing, and post-pruning, it trims a fully grown tree. That is the main difference. So mainly post-pruning is often preferred because it is easier to find out the right balance and can lead to a more effective tree. So based on these things, here is a small example. So this image is showing an unpruned tree which is on the left and a pruned tree on the right. So this unpruned tree is complex with multiple levels of splits and many leaf nodes, and the pruned tree is smaller and less complex. For example, it has removed this branches from node A3 on the right, placing them with a single leaf node for class B. So this suggests that the further splits from A3 were likely due to noise and didn't contribute to the tree's overall performance. So prune trees are preferred because they are simpler, faster and more accurate. Simpler in the sense it is easier to understand and interpret, faster it is quicker to make predictions, and more accurate in the sense better. It is better at classifying new independent data because they focus on the most important patterns rather than on random variations. So that's all for this session. Thank you.